Hi all, in this video we're going to see about measurement of renal blood flow. So these two questions, that is measurement of renal blood flow and measurement of GFR, is usually asked for the exams, and the important point is in the difference in the indicator that is used for both. So we'll see how the renal blood flow is measured and what are the different calculations involved. So first of all, we know that renal blood flow is essential for filtration, reabsorption, secretion, as well as homeostasis of BP and electrolytes. But how can we measure the renal blood flow? We cannot do it directly, and that is why it is estimated by physiological principles. So the most important physiological principles that we use is the Fick's principle. So based on the Fick's principle, the blood flow to the organ is equal to the amount of substance taken up or removed per minute divided by the arteriovenous concentration difference. So we'll come back to the Fick's principle again. Once I explain the concept, all this will be very clear. Now let's talk about what indicator should be used. So see, basically by Fick's principle, we are using an indicator, and then using that we are finding out the organ blood flow. So to find out the renal blood flow, which indicator would be ideal? So the indicator to be used should be freely filtered in the kidney, not reabsorbed, not fully, it should be fully secreted, not metabolized or stored, not produced by the kidney. It should be measurable in the arterial and the venous blood, and it should not alter the renal hemodynamics. So these are the properties that are required for an indicator when it is used to measure the renal blood flow. And such an indicator substance that is usually used is PAH, or para-aminohippuric acid. Well, that is because it is fully filtered and secreted, and almost 90% is removed in one pass. See, that is important because we want the indicator that we use to measure renal blood flow to be removed in one pass. So even though it is not that ideal, 100% is not removed in one pass, but still approximately 90% is removed in one pass, which means the venous PAS, there will be nothing in the renal vein. Okay, so venous pH will be approximately equal to 0. So I think this is better explained with the help of a diagram. So suppose this is our kidney, wherein we can see the renal artery, the renal vein, as well as the ureter. So if a substance enters the renal artery, it will reach the afferent arteriole, it will reach the glomerulus, and from there, depending on the property of that substance, it can either be fully filtered, or it can be reabsorbed, or it can be secreted, and depending on what happens there, that substance can be present either in the renal vein, or it can be fully excreted via urine, or it can be present in both. So here our substance is pH. So the amount of pH that is entering the artery after this filtration and all, it can come out either through the renal vein, or it can be excreted in the urine. Now we said that approximately 90% of the pH is fully secreted, which means that whole thing around 90% is going to come out through the urine. It's only very less that is going to be present in the renal vein. So for smaller concentrations, we can almost neglect that the amount that we can assume that the amount of pH in the renal veins are going to be 0, which means the amount of pH in the arteries is going to be equal to the amount of pH in the urine. So when I say amount of pH, what does it actually mean? It means the concentration of pH in the arteries into renal blood flow, that is the amount of pH in the arteries, that should be equal to the amount of pH in the urine, or the concentration of pH in the urine into urine flow rate. Okay, so concentration of pH in the arteries or in the plasma, as whatever you say, into the renal blood flow is equal to the concentration of pH in the urine into urine flow rate, which is depicted by V. So from this we can understand the renal blood flow. Renal blood flow would be urinary concentration of pH into V divided by arterial pH or plasma pH. So while we were happy with the derivation, the scientist pointed out that there's one problem. See, we are not, the thing that is filtered is plasma. RBCs are not involved, so how can you call it renal blood flow? What you're getting is just renal plasma flow. Okay, so that is why we modify it as renal plasma flow is equal to urine pH into V divided by arterial pH or plasma pH. So that is our formula, right? So while we were happy that we got the formula, Some people said that, hey, you cannot say that it is RPF because here in this case you assumed that the venous pH is 0, but actually it's only 90 percentage was only excreted by urine. You've got some remaining. Okay, so you can't say this as this is renal plasma flow. You can say it as it is effective renal plasma flow. So that is ERPF is urine pH into V divided by arterial pH or plasma pH. So what is RPF then? RPF should be corrected for this. So RPF is ERPF divided by 0.9 to tell that 90%, only 90% has been excreted out. Okay, so it is like this that we get the actual renal plasma flow, right? Now from this renal plasma flow, we have to find out what is a renal blood flow. So for that we have to correct it for that RBC component. So that is why we have another formula, RBF is equal to renal plasma flow divided by 1 minus hematocrit. HCT stands for hematocrit. So first we find out, we give pH, find out the concentration of pH in the urine, multiply it with the urine flow rate, divided by the concentration of pH in the arteries. And then that value divided by 0.9 will give you the renal plasma flow, and that value divided by 1 minus hematocrit will give you the renal blood flow. So that would be a final derivation. Okay, so as I said, the pH clearance is not exactly 100%, 10% is not removed, so we have to correct it with the extraction ratio, which is approximately 0.9. So the true RPF is equal to ERPF divided by 0.9. So normal value is around 700 milliliters per minute, and the blood contains plasma and RBF, so we'll have to correct it for hematocrit. So RBF is equal to RPF divided by 1 minus hematocrit. So suppose we get the RPF as 700 and the hematocrit is 0.45, then when you substitute you will get this value. Okay, so what are the formulas? Effective renal plasma flow is urine pH into V divided by plasma pH or arterial pH, and the normal value for that is 625 milliliters per minute. The actual RPF, the renal plasma flow, is that divided by the extraction ratio, which is usually 0.9. When you substitute, you will get this value, 689 ml per minute, and RBF is equal to RPF divided by 1 minus HCT, and when you substitute it, you will get it approximately as 1300 ml per minute. So we'll just now try practicing substituting these formulas. So suppose the subject is given an infusion of pH and following data is obtained. Urine pH is 12, urine flow rate is 1, plasma concentration of pH is 0.2, extraction ratio 0.9, hematocrit is 40%. What is the renal blood flow? So you can try doing this sum and substituting. First we have to find out the effective renal plasma flow. For that, substitute the values. You will get a value like 600. Then you can find out the true RPF by dividing it by the extraction ratio, and you will get the renal blood flow when you substitute it for the hematocrit also. RPF divided by 1 minus hematocrit. So you will get it as 1112 ml per minute. So this is how you will find out the renal blood flow. So I hope now that the concept is clear, and I hope this was useful for you. Thank you.